Many students try to memorize the Born-Haber cycle as a fixed diagram, but it is much easier if we build it step by step. In this video, we will use sodium chloride as an example and slowly construct the enthalpy level diagram. The Born-Haber cycle is just Hess Law applied to ionic compounds. We compare two roots that begin with the same elements and end with the same ionic solid. We start with the elements in their standard states, sodium solid and chlorine gas. Be sure to include the state symbols. We end with sodium chloride solid. These two levels are the beginning and final product of the cycle. The direct route is the standard enthalpy change of formation of sodium chloride. It is exothermic, so the arrow points downward. Sodium chloride is more stable than the separate elements. Now we build the indirect route. First, sodium solid is converted into gaseous sodium atoms. This is atomization of sodium. Energy is absorbed to separate sodium atoms from the metal lattice, so the arrow goes upward. Next, chlorine molecules are converted into chlorine atoms. Since sodium chloride contains one chlorine atom per formula unit, we use half a mole of chlorine molecules. Sometimes you may even see this formula. Half Be, which stands for bond energy, equals to 1 times the standard enthalpy change of atomization. Breaking the chlorine-chlorine bond requires energy, so this step also goes upward. Now, the gaseous sodium atom loses 1 electron to form a sodium ion. Removing an electron always requires energy because the electron is attracted to the nucleus. Therefore, first ionization energy is positive and the arrow goes upward. The electron lost by sodium is gained by chlorine. When a chlorine atom gains an electron, energy is released because the electron is attracted to the chlorine nucleus. So the first electron affinity is exothermic and the arrow points downward. Finally, the gaseous sodium ions and chloride ions come together to form the solid ionic lattice. Strong electrostatic forces of attractions are formed between oppositely charged ions, so a large amount of energy is released. This is the lattice enthalpy of formation. For UK syllabus, this is also known as lattice energy. Now, the full diagram is complete. The direct route goes straight from the elements to sodium chloride. The indirect route first forms gaseous atoms, then gaseous ions, and finally the ionic lattice. Since both routes have the same start and end point, their total enthalpy changes must be equal. Using Hess's law, the enthalpy change of formation is equal to the sum of the steps in the indirect route. If lattice enthalpy is the unknown, we simply rearrange this equation. Substituting the values, we get negative 411 equals 108 plus 121 plus 496 minus 349 plus lattice enthalpy. The sum of the known indirect steps is positive 376. Therefore, lattice enthalpy is negative 787 kilojoules per mole. The most common mistakes are forgetting the half in front of chlorine, using the wrong sign for electron affinity, confusing atomization with bond dissociation. So please remember this equation. Half Be is equals to atomization energy for non-metallic elements. And mixing up the lattice enthalpy conventions. In the US, lattice enthalpy is defined as endothermic. But for the UK syllabus, lattice enthalpy is defined as exothermic. But the biggest mistake is trying to memorize the diagram blindly. Build the diagram from the chemical changes, and the arrows will make much more sense. Here's the final takeaway. The Born-Haber cycle follows a simple story. Start with the elements first, then make gaseous atoms. Next, form gaseous ions, and finally form the ionic solid. Once you understand the journey, the diagram is no longer something to memorize. It becomes something you can build. If you want to learn more about A-level chemistry, be sure to subscribe to this channel, and I will see you in the next one.